Okay, so mic is on, yeah. Thank you for the wonderful introduction. So I want to thank you all for coming here to this session. You know, as you might imagine, or as you may have guessed, you know, I'm not from Australia. I'm not Australia-based. I came here from Croatia, Europe. And as you probably may guess, it's like a pretty long trip. Here it took me like something like 24 hours in total, maybe a little bit more. And still somehow it feels like it took me much longer to get like from the main conference hallway to this room, you know. And so I want to thank you all for coming down under here to the Blue Room, you know, to the talk on concurrency. And as a thank you gift, you know, I'm going to give you a lot of information. You know, I have prepared a lot of stuff for you. So I'm going to speak very fast, and I apologize about that, but I hope you know, like this is done because I'm hoping that I'm going to give you more value, you know, for your time. So concurrency is the main character of this session, of this talk. And this is a topic which is, I would say, like pretty painful, traumatic in software development. You know, as engineers, we have developed like this large collective, I would even say rational fear of concurrency. And you're going to hear many developers saying that, like, you know, concurrency is difficult, it's hard, especially more experienced ones. And they're going to, you know, they're going to caution you against using it. They're going to tell you that like, here be dragons, don't go down that path. They're going to tell you the stories about race conditions, and they're going to tell you stories about deadlocks and whatnot, you know, and talk about their own painful experiences. And this is all rooted in practical experiences of many, many, many people, you know. So this is real advice. But still, you know, with this talk, I want to propose a somewhat different theory. I want to seek a somewhat different truth, if you will, that, you know, perhaps the problem is not in concurrency itself, but that like the concurrency is not really as difficult or nearly as difficult as we can be led to believe or as we can be conditioned into thinking, but rather that the tools that we are typically given to work with it are pretty basic, pretty elementary. You know, they don't really rise up to the challenge, and as a result of that, our job of working with concurrency becomes way more difficult than it could or should be. You know, and so in my experience, like if we actually have a good tool in our hand, the one like that has been designed and built for this job, then, you know, this challenge of managing concurrency becomes a fairly straightforward, mundane thing, if you will. It becomes something you can do and still keep your sanity in the process. It can become something that you can like use extensively and still be able to reason about the correctness and the behavior of your programs. And it can even become a job that you can enjoy. Perhaps most importantly, like when you have a good tool, then your fear from concurrency will diminish or completely fade out. And as a result, you're going to see a lot of potential for concurrency in the places you haven't seen before. You do not have to be like this tall or that wide to have the need for concurrency or to profit from it. And this is perhaps the most important point I'm trying to drive with this talk. So for me, this tool has been the thing which is called Beam. Which is the Erlang virtual machine, and this is the runtime home to programs written in languages such as Erlang, Elixir, Gleam, and others. And this thing has been built since its inception, like more than 30 years ago, with a strong focus on massive lightweight concurrency done in a sane and an approachable way. This is the challenge it has been solving in production in large companies, as you have heard in announcement, you know, for like 3 decades. So it's like pretty mature, battle-tested, stable technology. But make no mistake, it's also quite usable and applicable in simpler, smaller situations. You do not, again, you don't have to be like super scalable or operating on a large scale to have the use of it. And so what I'm going to do today, today's agenda is I'm going to give you a quick intro to Beam-style concurrency. And then the main course is going to be a set of explorations of Beam concurrency in practice. So we're going to take a look at a couple of examples taken from the real-life projects that I've had the pleasure of working on. And these examples are going to fall like on the simpler side of things or on the lower scale side of things, with the intention of showing you that even in such situations, there's a lot of room for concurrency, that it can be done in the same way, and that we can profit from being concurrent. So buckle up, a lot of stuff ahead of us, and let's kick off with a basic intro to Beam concurrency in 5 slides. So the central idea here is a thing which is called process. And process here means a Beam level concept. It's not an OS process, it's not an OS thread. I'm going to clarify this like in a couple of slides. Essentially, process is a sequential program. You know, just a bunch of instructions or expressions executed one by one. And at runtime level, like, you know, when you use some Beam language, every piece of code runs inside some process. And from within a single process, you can start or spawn additional processes. right? So here we have like a sketch of one sequential program. We invoke some standard library function. We spawn another sequential program, pass it a function which is going to run independently in that other process, and that's it. Two notes that I want to say here. So this code sketch and all the code sketches are going to be done in Elixir, but doesn't really matter. It could be any other Beam language, such as Erlang. I'm talking about runtime level properties here. Note number 2, I'm going to stick to the lowest level primitives, such as spawn. We rarely use those things in production directly. We use some higher level abstractions that make like the whole code look a little bit more declarative and take care of some special cases for us, you know. But again, I'm trying to drive like the fundamental principles here, and so I'm sticking to the lowest level abstractions. Okay, so we have spawned one process, and as a result of spawning, of invoking the spawn function, you're going to get a thing called PID, or process ID, and this is a piece of data which somehow uniquely identifies the process inside your system. And once you have the PID, you can interact with the process. You can send it messages. And this is also known as message passing concurrency. So these processes, they are logically speaking independent programs. They share no memory. We don't use like shared memory and locks and whatnot, you know. So they're like completely isolated from each other. And the only way they can coordinate is by sending themselves messages. So to send a message, you need a PID of the target process, and the message is an arbitrary piece of data, you know, whatever term you can construct. You invoke the function send, and as a result, the message content is placed into the mailbox of the receiver process. So each process is at runtime level associated with a mailbox, which is a FIFO queue. So the message goes to the end of that queue, and then immediately you move on. So the send doesn't really wait for anything else. You move on to the next instruction. On the receiver side, you can use this receiver expression to pull one message from your queue, or to wait for it if it's not there. And that's it. Those are your primitives for implementing cooperating processes. At the runtime level, what's going to happen is, so you're going to have like a project, you know, a folder structure of files in whichever language you're using, like Elixir or Erlang. You're going to somehow compile this project and somehow start it. And at this point, a single OS process is started. This is the instance of Beam, and inside that single OS process, everything is running. So inside that process, you're going to have a bunch of these little yellow boxes, I call them, these processes, these small sequential programs, which you spawn on your own from within your code, and you're typically going to have a lot of them. Like in smaller systems, it's easily going to be like a few hundreds. Medium to large systems, like hundreds of thousands or even millions. These things are like very lightweight, super cheap in terms of startup time and memory overhead, and we're not afraid of using them. We use them like in abundance. This is to me what I would call Beam style or Beam concurrent philosophy, you know, and I'm going to try to demonstrate this. We don't use them randomly though, so there is like some logic behind it. So either way, you're going to have like a bunch of these processes, and then internally behind the scene, the Beam itself is going to spread the execution of those processes across available hardware. So like a very simplified version is you're going to have a couple of OS threads called schedulers, which are executing your processes. By default, there's one scheduler per available CPU core. And like in a naive version, you can think about it as if each scheduler picks one process, runs it for a little while, then puts it back to the queue, takes another one, and so on and so forth. Right? And so this makes your system immediately multi-core capable and vertically scalable, but again, we don't care really about thread pooling or such stuff. We don't think about that. We think about processes. And so that's it. That's all we have. Like pretty simple stuff. Obviously, of course, I didn't tell you everything. I'm going to drop a couple of more features down the line, but it's like fairly simple stuff, yet super powerful, very versatile. And so we're going to take a look at a couple of examples, and as a warm-up, I'm going to take something pretty simple. I'm going to take a scenario of execution of a long-running task. So this would be like a class of examples or class of situations where like you need concurrency irrespective of your scale or complexity. So in the particular case I'm going to present, we were building a data analytics or privacy-sensitive data analytics system. So in like this diagram, that would be the thing in the middle, which I'm calling app here, you know, just for the sake of brevity. Essentially, our clients or our customers were companies that built their own product, and people were using that product, and as a result of using that product, there was some database with a bunch of data, and they wanted to do some analytics on top of or from this data, like gather some insights, correlations, and whatnot. But they didn't want to invade privacy of the people who like use their own product, and this is where we came into play. So basically, our system would be installed on client premises between the analytics, so the people who were like actually using or trying to gather some insight, and the database on the other side. And so the analytics would like send us an SQL query, And we would basically return the result of that query, making sure that nothing in this result reveals anything sensitive about any individual. You can ask me after the talk how we did this. It's like pretty interesting and very smart thing. But either way, like executing this query now becomes like a pretty potentially long-running activity, right? So like in simpler cases, it was taking for a couple of minutes. It could easily, occasionally take like over an hour. And this is an example of stuff you don't want to run sequentially together with everything else. Because if you do, then everything else is blocked, and no one can like interact with your system for a single hour or so, right? So that doesn't work. So you need concurrency, no matter your scale. Like our scale was per installation, a handful of analysts using the system, issuing a handful of queries per day. This is by all means ultra low scale, yet we need concurrency, So let's see the process structure. I'm going to focus on two processes in this implementation. So the one which I'm calling analyst kind of models or holds the connection or a session of an analyst to our system. Like you can think of it as it like owns the network connection, literally, like the WebSocket connection, for example. And so whenever it receives a request from the browser or like from the remote client, typically it would be a browser, like do this, do that, then it's going to do something. So when it receives a request to do the query, to run the query, then it's going to spawn the query process, right? So we're not going to run query inside the same sequential program as the analyst. We're running it separately, compute our result there, do our magic there, and then return the result as a message to the analyst, which then ships it over the wire to the other side. And by doing this, we liberate or decouple the execution flows of these two programs, right? So the analyst can still interact with the system while the query is running, and perhaps they can start additional queries, which was occasionally the case, of course. And just like that, of course, the other analysts may interact with the system while some long activity is running. This is the basic motivation behind separating things into processes. You want to separate their execution flows. So let's take a look at some code. Like, it's pretty straightforward stuff, right? So you want to run the query separately in a separate process. You spawn the process. You run the query. A lot of magic obviously happening there. Either way, you compute the result somehow, and then you send the result to the analyst PID, and now you're done. This process is now done. And so this run query thing, one important thing to note about that is that like a lot of stuff is happening there, and it's both I/O and CPU bound somehow at the same time. So we need to fetch the stuff from the database, and we need to do some of smart mathematical post-processing calculations to provide our guarantees. And we cannot do this like sequentially. We cannot like fetch stuff and then do our magic because there's a lot of data in the database. So we're streaming the data and processing it. And I/O and CPU boundness is intertwined, and we don't care. Like, so we use Spawn to separate this separate activity from everything else. Unlike in many other technologies, where you have to choose, like, am I doing I/O-bound thing or am I doing CPU-bound thing, and then either go for like future promises or async await versus some sort of thread pooling. And this is like, wouldn't even work here. So we don't care. We have like one abstraction that does the job for us. I want to separate the execution of two things. I'm going to use that abstraction. Right? Very important point. Makes my job much, much easier. So the analyst process. That one is going to be written in the following style. This is like a very simplified sketch. Again, very low-level sketch. Typically, we would use some higher-level abstraction that makes this stuff more declarative. But the gist of it is this is what we call a server process. Very important thing. It's like the style in which we write most of our processes. It's like a reactive style of, or event-driven style of programming, if you will. Essentially, a server process loops. In each step of the loop, it waits for the message and then does something with the message, then rinse and repeat, wait for the next message. And so it's like a single-threaded or sequential server where requests are sent as these messages, right? And this process may also maintain some state, some arbitrary piece of data which changes over time as a result of handling these messages. So yeah, that's a little bit vague and generic, so we're going to take a look at some examples of what kind of messages are we handling in the analyst process. So for example, this will be one kind of message. We are receiving the message, and receive is also kind of like a switch case statement. So if the message has like this shape, run me some query, then we're going to do some logic. And basically we're going to receive this message as a result of decoding bytes, which we receive via WebSocket. We somehow decode them into this structured message. And then we do the switch case. Like if the message is run query, then I'm going to run a query. Running a query means I'm going to spawn a process and do all that stuff that I've shown you before. The result of that is the PID of the query process. I store the PID in my own internal state. I'm keeping the track of the queries I have started, and then I loop to await for the next message. That's it. That's all. Another kind of message is the result of the query, right? So the query process is going to send me the result back. Typically, it's going to contain, at the very least, the PID of the query process itself, together with the actual payload or the result. And now I can report the result. I can remove the query PID from my state, and I can resume the loop and await for the next message. And that's your happy path for doing asynchronous query execution or long-running task execution. Crashes, right? Things will go wrong from time to time. So again, you know, we're doing a lot of I/O for a long amount of time. We may lose the connection to the database. In the process, we are doing a lot of fancy computations. So we may like have some bugs, do like division by zero, square root of a negative number, stuff like that. You know, when those things happen, an unhandled exception happens, and like in any other program, a program crashes when it's an unhandled exception. But the thing about Beam is that this crash is confined to that single concurrent small program, right? And so a crash is not an abrupt event, and this is your basic primitive for implementing fault-tolerant programs or systems which are resilient to individual failures. Like the overarching idea is the more aggressive you are in splitting your job into small, semi-dependent or independent processes, the less of negative effects there are when some things go wrong, you know, because the thing is not too big to fail, right? So you mitigate the negative effects of failures. You're going to see an example of this a little bit later on. But either way, the crash is not an abrupt event, and yet at the same time, it's also not a silent event. So any other process in the system may be notified if some other processes crash or terminate, right? And this is how we write fault-tolerant programs. You know, you write one thing to do the job, another thing to respond to the failure of that thing, right? So in our particular case, the analyst process is somehow going to ask from the runtime, you know, you invoke some function. I'm not showing you this. There are like a couple of different ways, but those like mechanics. The principle is relevant, right? So the analyst process is going to, when it spawns the query, it's going to ask the runtime, like, let me know when this thing stops. And then you're going to get a message. The process with the PID foo has terminated because of the reason bar. Right? And then you do the conditional logic and you do something while handling this message. So like this exit reason or termination reason, it can be normal. You know, the process has ran its course. We have exhausted all of the instructions. And then we're not going to report anything because we have already done this like 2 slides ago. If the reason is not normal, then it's subnormal. So some crash has happened. Typically, this piece of data is going to contain like an exception message and a stack trace, and we report this like a generic message for the user, more detailed one for the operator, and you're good to go. Irrespective of the reason, this is the place where I would remove the query from the state, not like the 2 slides ago, the happy path, because here we end up no matter what, right? So this is where I'm removing the query. It's not running anymore, and again, I resume the loop and await for the next message. And this small example demonstrates what to me is the gist of concurrent thinking in Beam. You know, how we split things into processes, right? We split things to separate their execution flows and or their failures. Basically, like if you have 2 functions, foo and bar, and you're wondering like, do I need 2 processes or 1? Like the guideline would be if you don't want the duration of foo to affect the duration of bar, and or you don't want the potential failure of foo to affect the success of bar, 2 processes, else 1 process. And like there are going to be some exceptions, but this is like a very good guideline to start with. On a more higher level of thinking, I like to describe this as you want to run separate activities of your system, logical activities in different processes. That's the general idea. And now we're going to take a look at a little bit more involved example of that style of thinking in the scenario which is data processing pipeline or ingestion pipeline. And this is like a class of problems where I think that Beam and Beam languages really shine. They're like a really, really good choice of technology for those kind of things. So in particular case, what we were doing, we were building like this service. Again, it's the thing in the middle that consumed a stream of events from a bunch of different data sources. And these events were describing sport matches which are currently taking place. And you know, we would have to interpret each event and continuously maintain our own view of the world, our own model, you know, that fits our purposes. And as a result of each update to our own model, we would have to make some updates to our own internal database, which was used by a bunch of other services, as well as ship this data, this new model, to the remote web server that serves this data to the users, right? So this is like a small example of your typical consume, process, produce service, which you've probably seen if you've done some event-driven microservices. And so how do we implement this pipeline in the Beam language? It's like this, Basically, you're going to have like one process. These are going to be server processes, right? All of them. You're going to start them statically during your boot time. And each process basically waits for the message from the previous in the pipeline. Then when it gets the message, it does its own job, produces the outcome, sends it as a message down the line, and you're good to go, right? And so at the top, we have these feed processes. So these are the processes which connect to the remote external services, and they're receiving feed of events. They literally receive bytes, and their job is to convert bytes into structured messages, which we can understand, right? And then you have the model process, which interprets each message, applies it to our own model. And this is our point of synchronization, our point of consistency. Remember, again, that the process is a sequential thing, right, a sequential program. So this is where we handle one message at a time. And once we do that, then we spread out. We can spread out again and do our updates to the database independently from sending this stuff down the wire to the server. So in terms of boundness, again, like this feed, there will be a combination of IO bound plus CPU bound work. Database, pure IO bound mostly, server, sending to server, CPU plus IO, because we have to encode to JSON and then send it down the wire. Model, pure CPU bound stuff. We don't care. We just use, I don't care about these things. That's like way too technical for me. If I want to run things separately, I'm going to use separate processes, and this is all I care. And the runtime does the rest for me, as it should. The model thing itself, so that's an interesting stuff. The model is basically for us a collection of matches, sport matches, and these are like completely independent of each other. And so rather than having one mega model, we're going to have like per match model. We're going to have like these dynamical processes, which are like pretty straightforward to do. Essentially, when I get the first message for a particular match, I'm going to start the match process, and I'm going to keep it alive for as long as I'm receiving messages for that match. And somehow I'm going to then, wire or forward the proper event from the feed to the corresponding match. I'm going to come back to this in the next slide. And so now, because this update to the model is CPU-bound work, now I'm have a lot of potential for spreading the work across available CPU cores. But even on a single core machine, this is going to work much more efficient, because for each event, the active data set I'm working on is much smaller. It's just a single match rather than a bunch of them. So in particular, the garbage collector is going to be much more efficient, right? So in Beam, GC is done on a per process level, not on the world level. And what this means is that when the process is in the scheduler, and it has some scheduling time and it runs some instructions. If it needs to expand memory, if it needs more heap, then prior to that, a GC is going to be done for that process alone. And that GC is going to analyze just the active data of that process. And this is just a single match, right? So it's much faster. It's going to be way more efficient, and you're going to have less latency, and you're going to be way more efficient in keeping up with real time. Most importantly, a failure when processing a single match is going to affect that match alone, right? And we had that situation. We had a bug, as you do, of course. It happens from time to time. So there was a particular set of constellations of circumstances where a single event applied to a single match would trigger a crash, and that match crashed. We weren't able to proceed forward until a human came and fixed the bug. But in the meantime, all of the other matches are still working. And if you have 100 matches, you still have 99% of your service, which is way better than nothing, right? So this is how you build fault-tolerant programs or systems. How do we discover a particular match, right? So this is the registry pattern, which you may have seen if you've done service-oriented architecture, especially microservices. And I'm showing it here as an example of how we do those things at a much finer-grained level, actually. You could say pico or nano services directly in our language without needing to use etcd or stuff like that. Basically, you're going to start a single process which acts as a registry, which has a mapping of logical role of the process to its physical address, which is the PID, And you're not going to have to implement this yourselves, right? You're going to use an off-the-shelf abstraction, which is, of course, in Elixir, it's available in standard library. And then what's going to happen is you're going to start the match process. It's going to announce itself to the registry, I'm the process responsible for the match 1 to 3. Registry stores this mapping. On the other side, the feed process decodes the incoming message, reads up some match ID field, then asks the registry, like, who is responsible for this process, gets the PID, and now it can talk to that process, right? So that's it, your basic registry pattern or service-oriented pattern directly here in your language of choice. Managing the load in this data pipeline is also an interesting thing. So I would say that like load control is the essential challenge of any sort of data pipeline. So here we have like one example of that. We have like these match processes, and again, every time we update the match, we have to send something to the remote server. It's depicted here as a dispatch process, right? So basically what we're sending is like the new state of the model together with the diffs that bring the previous state to the next one, right? And this is what we need so we can serve the data to the users, that use the stuff via browser. So dispatching this basically means we need to encode to JSON and then send it down the wire over the network, right? This is a potentially long-running activity, and when we did this, like on every single incoming message, we would quickly fall behind the reality. This wasn't really efficient, even on a smaller load. So like I would say this service was moderately loaded. We had to deal with, in normal modes of operation, like few dozen messages per second, peak times few hundred messages per second. This isn't small, but it isn't exactly what I would call like super high, but still, even with that load, very quickly we would fall behind. We weren't able to like ship the stuff one message at a time. The solution to this problem is batching, essentially because like handling n things at once is way more efficient than n times handling a single thing. That's usually the case when you have networking involved. And so, to do the batching here, you just split the process into two, right? And you have like two distinct activities. You have the batcher and the dispatcher. So the batcher batches, it accepts it accepts outgoing messages, it aggregates them, occasionally hands them off to the dispatcher. Now the dispatcher does its magic, like encodes, sends it down the wire. Concurrently to that, the dispatcher may accept more work, okay? Just, you establish two processes and send them messages. The main challenge here is how often do we hand off this data, this batch, right? And like typically people go for the approach of picking the number X of like at most X messages plus at most Y seconds. The problem with this is that like what sort of numbers should I choose? So like if my parameters X and Y are too small, then my batch is going to be too small. And as a result, I'm going to end up with the same problem. I'm going to do like too frequent deployments or dispatches to the other side, and I'm going to fall back behind the reality. On the other hand, if these numbers are too large, then I'm going to wait for too long until I complete the batch. And again, I'm going to introduce an unwanted latency, right? And so I don't like these approaches. And what I like to do instead is the technique I called adaptive batching, which would be a sort of variation of demand-driven producer-consumer relationship. So we're going to focus on the batcher and the dispatcher here to explain this. So the batcher here is like the producer for the dispatcher, okay? Now the way this works is the dispatcher is going to come to the batcher, is going to say like, I'm available, give me some work please. And it gets from the batcher whatever it has at this point, unless it has nothing, in which case the batcher awaits for the very first message and immediately forwards it to the dispatcher. Okay, and now the dispatcher again does its magic. The batcher collects the subsequent outgoing work. Once the dispatcher is done, it comes back to the batcher, like, I'm ready again, what do you have for me? And it gets the next batch. Okay, and as a result of this, like if the dispatcher is faster than the incoming rate of messages, then we're actually going to have the batch size of 1, and it's going to work perfectly fine. When the circumstances change, which they will, most typically when the incoming rate increases, perhaps not so frequently, but still happens, like when the network becomes slower or the remote service becomes overloaded, less responsive, so that we cannot dispatch as fast as we are receiving new stuff. The batch is automatically increased to adapt to these circumstances. Once these circumstances clear up, the batch is automatically shrunk, and you don't have to worry about those numbers. Now, the reason why I'm showing you this is because, like, coming up with this algorithm and reasoning about its behavior is like super trivial. It makes me feel smart, but the reality is that like the good tool dumbs down the problem, right? So I basically draw these two boxes, I draw some arrows, and obviously, of course, I spend like a few minutes thinking about it, maybe discussing it with someone, and that's it. I can convince myself that this stuff works. I can reason about such things in a way that I couldn't when I was doing like classical multi-threading, okay? So the final thing I'm going to talk about is cancellation, right? And so this is the feature that, in my view, is like an essential feature of any sort of concurrency technology, and it's surprisingly overlooked by many, especially the ones aspiring to, compete for the same space as Beam languages. And it's also, I think, frequently overlooked by the developers assessing those technologies. So, like, I don't want just the ability to start the program. I want the ability to stop it. It's needed almost all the times. So we're going to take a look at 2 examples. So the simpler one, I'm going to go back to that data analytics query execution. So if you remember, we have like this long-running query, we're running it, and we obviously want to allow people to stop the query, to cancel the query, right? Like the analyst, may have decided like, oh, this query is wrong. I'm not going to wait for like 1 hour until it finishes. I'm going to hit the cancel button, and then I'm going to start the next one. And so how do we do that? It's as simple as one-liner. You need the PID of your process, and then you ask the runtime, can you please stop me this thing? And what's going to happen is then that process is going to stop with the given reason that we have supplied here. It can be an arbitrary reason. There are like a few special ones, but it can mostly be arbitrary. So this shutdown doesn't really mean anything to the runtime. It's going to stop the process, and we're going to get the message, process or this query has stopped with the reason shutdown, and now we do the conditional logic that we already had. So if the reason is shutdown, I'm going to report the successful cancellation. If the reason is normal, I'm not going to do anything. Otherwise, I'm going to report the crash, and I'm good to go. This is your cancellation. And I'm showing you this here because, like, again, in many other technologies, especially the ones based on CSP concurrency model, you're not going to have this. Like in CSP, your concurrent activities are anonymous. They are nameless, right? And so you cannot ask the runtime to stop the thing which you cannot name, right? And so as a result, you're going to have to devise your own manual implementation of cancellation. Typically, you're going to build like a communication channel, and then you're going to pass it around as something which is called context, or sometimes a cancellation token, and you pass it from function to function. And every now and then, you manually just ask, like, in the worker process, which like runs this query, am I being canceled? Am I being canceled? Am I being canceled? And if you are, then you have to manually unwind your stack. Like, it's very, very tedious and error-prone, and I don't see myself like doing that kind of work, especially not in this case. So, like running this query, this analytical query with our guarantees was a huge, like super complex piece of functionality, a lot of micro functions involved there, and like this wouldn't really work. Now, this is all well and fine, but in many cases, you want to also allow the process being terminated to say some final last words, like to drain whatever work it's currently doing, as well as clean up whatever resources it has to. And so this is also perfectly possible, right? Essentially, just I'm going to go back 1 slide. So I did this process exit thing. Technically speaking, we send an exit signal to the process. And by default, that process is just stopped in its tracks. But each process may decide to trap exits. Basically, you invoke this function and you ask the runtime, convert the exit into a message. And so now, when someone tries to cancel me, I get this at the end of my mailbox as a message, and I handle this message, by cleaning up my work and then, stopping myself with a given reason. And that's basically it. Most of the times, you're not going to really have to do this. So as an aside, like everything is process-oriented in Beam. So like memories connected to the process, when the process stops, it's immediately reclaimed, doesn't even go through the GC. File handles, network sockets, all stuff immediately, released. However, there are like some things that Beam cannot track, like if a process created some folder on the disk, then you're going to have to clean it up manually. And we're going to see a more involved example of that. The final one, which is the custom implementation or proprietary implementation of the continuous integration, right? So like when we were building our product, specifically that data analytics thing, we implemented our CI in Elixir rather than choosing something off the shelf. So not as a product, right? Just for us internally. We did it because we believed, and I personally still strongly believe that doing a CI with a language which is Turing complete, which like has a good support with tooling, which has a rich support for massive concurrency and deep integration with the underlying operating system, is way better than choosing YAML to deal with CI, right? Much more flexible, much more powerful, and this is what we did. And it was by far the most enjoyable CI that I have ever had the pleasure of working with. Now, we're going to take a look at the process structure of this CI. So at the top, we have like what we call a root process. This is the first process that started, right? Like your main process or main function, if you will. And from within that process, you're going to start additional processes, like your children. Those children are going to have their own children and so on and so forth. And this is what we call a process hierarchy or process tree, supervision tree more precisely. And I like to think of it as a top-down view of the activities of your system, like your top-down service manager or systemd, if you will. And so I'm going to focus on the hierarchy of a couple of important processes. So we have like this main process here, and it's going to have these children, which we call builds. A build is basically an instance of an execution of a single CI, right? So like I push something to the main branch, that's one build. You push something to your feature branch, that's another build, okay? So those are like very dynamic processes, and just by looking at this diagram, we can tell that like builds are running independently, concurrently, separately from each other, in parallel, if you will, right? So a single build is further divided into projects. Essentially, you know, our whole product was divided as, or organized as service-oriented stuff, not microservices, but we had like a couple of independently deployed services, and those are of course reside in separate projects, and we kept them all in a single mono repo because this is the way. And so when we would have to build, you know, we would have to build multiple projects. Again, you can tell from the diagram that it's all done concurrently. Now, just as an aside, you know, we wouldn't always be building all of the projects, right? So, like, this is an example of what you get when you own your CI in a proper language, you know. We would, like, remember the last known state, like in a cache. So when something new is pushed, we do a git diff and figure out which projects we have to actually build. So typically it will be like one or two of them at the most, like in most cases. So it vastly reduced our CI build, and as a result, you know, increased our feedback loop. So what does it take to build a single project? And this is the meat of the CI, right? So basically, you know, you're going to run a bunch of commands, like fetch me the dependencies, compile this thing, run some tests, run the linter, and so on and so forth. For us, it was all containerized, and so this is the process structure, or an example. Like if I want to start a container, I'm going to start a process that starts the container and keeps it alive. If I want to run the command, I'm going to start the process which runs the command, you know, like compile this thing. There's going to be one process. And again, what you can see from this diagram, that at such a fine-grained level, we had support for concurrency because we could, because it's super trivial stuff to do. Now, the challenge here is, how do we cancel a single build? This is like a very frequent challenge in CI, right? Like I push something to the main branch or whatever branch, it started in building, I push something else, and now I don't want the previous build to be running anymore. It doesn't really make sense, right? I want to cancel that build. And I want to cancel all this entire tree, subtree of the build. Because if I don't, I might fail to start another build if there is like some lock on the global thing such as Docker container name, or I might have some strange race conditions if they are both running at the same time, or like in the best case scenario, my new build is going to be running slower because the previous one is running and I'm not using its result anyway, right? So like I want to cancel this stuff before I start the new build. This is the essential challenge here. So the way we're going to do this is, again, all of these processes, server-style processes, very reactive, event-driven style of concurrency. And we're basically going to have custom termination in each of them. Like the way typically you're going to do with a higher level abstraction, you're just going to implement some function which is called terminated, and it's kind of like a destructor of your process, and you're going to do your cleanup there. And so the cleanup happens before the process itself stops. For each process which is a parent of other children, you want to stop your children before you stop yourself, and you want to stop them in the opposite order of the startup, right? Because the younger children may depend on their older siblings. Right? And so you're not going to have to do this manually. You're going to just use some off-the-shelf abstraction, and it's going to happen magically. And so when I ask the build process to stop, what's going to happen behind the scene, without me doing practically, you know, zero work, we're going to walk recursively to the bottom, to the right, and then we're going to unwind, stopping one process at a time until we reach the top. So this is the shutdown order, which again you get practically for free, and this is what you want to get, right? You don't want to leave dangling stuff behind. Now, in those leaf processes, the command and the container, this is where you're going to want to have custom termination logic. So command is like associated with an external OS process. It started like Docker exec something something command, and you want to stop that thing. A container started the Docker container, and you want to stop that thing before you stop the process. And so this is going to be like a 5-liner, something like that in each process. And you're going to implement that, and then canceling the entire build is as straightforward as sending an exit signal to the build process. And then what I'm doing in the next line, I'm awaiting for the confirmation that the build process has stopped, because it takes a while until, you know, this whole structure is taken down. So I'm awaiting until it stops, and now I know that after this point, my build is not running. None of the associated activities of these commands, containers, whatever I have started, none of the stuff exists anymore, and I can start the new build, and I can, you know, be confident that it's going to work as it's supposed to be working. And you're not even going to have to write this code. You're going to use like a wrapper, which is going to be one-liner, like stop in this process, please. Okay? So that concludes my talk, more or less. I've shown you a bunch of examples. I think, or at least a couple of them, like different kind of examples for Beam concurrency can be used. It's a very versatile thing, and I have barely scratched the surface, to be clear. And so, obviously we don't have the time for more examples.
Yeah, we have 10 minutes.
Yeah. Oh, okay. Wow, I was pretty fast. But either way, you may find more time perhaps to look at some other talks. So, like 2 years ago, I did a virtual one on YOW Lambda. And that's like pretty much the same style as this talk, except the examples are completely different. So it uses examples more from the web server domain. And so you may want to check that one out. And then as a sort of spiritual predecessor or some sort of foundation, it's this talk from GOTO, where I go into details about features of Beam concurrency, into more details than I gave you today. It's very demo-driven, right? So a lot of stuff I kind of try to showcase to make them more tangible. So you may want to take a look at that one as well if you can find the time. I'm also the author of the book called Elixir in Action, which specifically is focused on, showing you how you can manage concurrency in Beam using Elixir as a programming language. It's discounted with a given code at manning.com, and this code is also worth for the entire Manning catalog, I believe. So I'm not sure how long it's going to be valid, so grab that while you can. I'm also giving away a couple of copies of the book, so I have one printed version and a few coupons for free ebook versions. So if you want that, grab me or find me immediately after the talk. You can find my contacts down on the bottom, Twitter, and more recently I'm trying to go for Mastodon, but I'm still active on Twitter as well, open for DMs. So if you have questions, let me know. And this is all I had prepared for you, so thank you very much.
Thank you, Saša. This is the time for Q&A, so yeah.
That was a great talk. I have a question about the state you maintain. Is it generally in memory, or are you generally maintain somewhere else? If there is somewhere else, what sort of storage you recommend for systems like that?
Yeah, so this is like a very low-level stuff, and the state is maintained in memory. It's a data structure. You may decide, of course, if you want, to store it in wherever you want to, but nothing out of the box particularly is offered. Although, the whole standard library, especially of Erlang, Elixir is built on top of Erlang, right? So it relies on its standard library. It's not an implementation detail. You can use it. So Erlang itself ships with kind of an embedded database, key value database, if you will. So you don't even have to start that on the side. You can start this thing and store it. I actually talked about this in the about a lightweight version of that in this talk. I have an example where I'm actually persisting the state on the disk, so you can take a look at that. But yeah, whatever you want. It's pretty flexible, by default in memory.
What is the experience of trying to debug one of these multi-process Beam programs? Just because I can see from the start if even something as simple as a single command is a completely separate process, trying to track thread states across several processes and how they interleave. This is an excellent question. Yeah, thank you very much. So there is some sort of a debugger in Erlang, and I think more recently even Elixir has some of its own kind of quasi-debugging tools, which I've never used. And I've been doing this stuff for more than 10 years in production, right? So this is essentially, I didn't talk about it, this is distributed system we're talking about here. In Erlang, concurrency and distribution are one and the same. I didn't talk about support for true distribution on multiple machines, but it uses the exact same mechanism. You can connect multiple beams into the distributed cluster, and you use those same primitives, I'm going to spawn, I'm going to send, doesn't matter where the pit points, so is it the local stuff or remote stuff. Now, I'm saying this because you're dealing with distributed problem, and then the solution to this is, observability, right, and metrics. So you want to log, you want to make sure that you have as much information as possible so you can figure it out, what happens. Because this stuff runs independently. I cannot debug one process while all others are, waiting. So essentially, this is like debugging a set of microservices that are independent.
Yes, you could say like that, but it's all integrated, so you have a much easier time. To me, this is way superior to microservices, although it doesn't cover exactly the same scenario. There are some overlaps, But this is, first and foremost, more aggressive. I don't think you would be doing microservices like having one microservice per match, for example, or dynamically started microservice. This goes like into much finer-grained stuff. But there are essentially the same set of challenges. If you think about them, except everything is here like available in your language, so it's, I think, much easier to wield compared to microservices. So I want to say again, because you have this with microservices, unlike with microservices, you don't have to be this tall to use this stuff. Yeah, debugging approach, definitely. I kind of trailed off to some other rambling, sorry, yeah. Okay.
Any other questions?
Yeah, behind. You have behind you.
Thanks for the presentation. May I know whether this model is only available in this Erlang language, or is it like a common model that's available in other languages as far as you know?
Sorry, can you repeat this? I didn't quite understand.
This messaging model that you showed us today, is it only available in the Erlang language, or is it like a common model available in other languages as?
So this messaging model, is it exclusive to Erlang? Yeah, no. So there are like, first and foremost, there are like some implementations that are inspired by Erlang, most notably Akka, for example, which you have in Java, and I think you have even in .NET, something like that, right? So that's when it's completely inspired by it. It is sometimes said that this Erlang style concurrency is actor style concurrency. I used to say this myself in my early days. But the thing is that like the inventors of Erlang, they said explicitly they didn't know about actor concurrency when they invented this stuff back in the late 80s. On the other hand, I also found someplace that the inventor of actor model explicitly said that Erlang isn't actor implementation. So I'm not saying that, but it's often referred to as an actor-style concurrency either way. As far as Go is concerned, or other CSP concurrency, it's a somewhat different style. So in there, you have like communication channel has the identity, but your concurrent activity doesn't. You can simulate one or the other, one with the other, or vice versa to some extent. But I gotta say to me, and I'm not invested in these technologies, I'm just a user. I did a little bit of Go, did a lot of Erlang and Elixir, and to me, this model is more far superior for writing concurrent fault-tolerant systems than what Go does, or what CSP does. I want my activity to have an identity, but either way, it is kind of similar because it's still like this user space concurrency, massive lightweight style concurrency. Yeah.
In the example of the child process cancellation, it works fairly simply in a stateless process, but when you have side effects on that child process before the cancellation occurs, how do you normally deal with that?
When you have the side effects before the cancellation occurs, what do you want to deal with? Like, do you want to clean them up, or?
That's the question.
So that's what I did with this CI thing. So that was like pure side effect, if you will, right? So like running a single CI instance means like we're starting some Docker container. That's a side effect. We're creating some folders for the cache and whatnot. That's another side effect, right? So we would definitely be implementing custom termination to, clean up whatever garbage we had. In particular for caches, we actually drained the current command. So we would have, even if the build is canceled, whatever we have come up with at this point, we would keep in the cache, unlike most other CIs. Because it's stuff on the disk, so if anything has changed, it's going to be recompiled anyway, right? But we again, this is what you get like when you use proper language for CI rather than a black box driven by YAML,
Mine was going more to a mutation on an external server.
Mutation on?
So if you were to send a message to somebody else.
Oh, okay. So if you send a message to someone else on a remote server, like a remote service or whatever, like if it's a database, of course you want to keep it in transaction, for example, so that's going to work fine. As a result of just terminating the process, as I said, the sockets are process owned, so the socket is closed and then the transaction automatically aborts. If you're sent to some messaging, like say to Kafka, then you send it, basically you need to do like a saga pattern, right? So it's a classical distributed problem that you have done, right? But you have them, in Beam languages, you have them already early on, in a good way, I would say, like, so it becomes easier to think about it. But yeah, if you did a side effect, you got to revert the side effect then, right? Somehow.